So my name is Dima Kozakov, and I'm at Stony Brook University, and in the Laufer Center for Physical and Quantitative Biology, and my lab is interested in method development for modeling macromolecular interactions. So before that, I was mostly working on modeling protein-protein and protein-peptide interactions, specifically global interactions. And right now, I was interested to see how our methods with some adaptation can work for small molecular docking. So basically, what we are trying to do is to have a global approach for global docking. So whereas most of the approaches focus on defining some box around the ligand binding site to do some localized docking, FFT type approaches, as I will describe in a little bit, potentially can explore global interactions. So basically, I will start with an overview of what we were trying to do in this round, and then essentially describe the results. So basically, our approach consists of several steps. So first, we are doing a global grid-based search where we can actually do the sampling of protein-ligand interactions on the grid, all over the protein surface, followed then by finding most likely regions where the binding happens, and starting some refinement using Monte Carlo from those starting positions. And for this round, since it was self-docking exercise, we knew about the positions of the waters provided in the crystals. So we rescored our highest ranking poles.
We have almost finished.
So we score it with the so we rescore the water with this rescores the poses, high scoring poses with waters, and after that we did the redundancy clustering and reported the lowest energy poses and use them for reporting. So just briefly give you an idea, since it's kind of a different method what typically is used in ligand-based ligand docking community, I give a short overview. So what we are doing, so basically the idea is that if you have you put receptor and ligand on the grid, and if you can express interaction potentials in forms of cross correlations, you can calculate them very effectively using fast Fourier transforms using convolution theorem. And what my lab was working for quite some time was actually expressing an accurate energy function, grid-based energy function, which was so far mostly validated on protein-protein interactions, and we did have some also protein small molecular applications. So the next step just to see, to give you a brief idea how this approach works. For example, electrostatic is a natural correlation or convolution. You have on one side you have a grid of electrostatic potential, on another side you have charge, and this is a natural cross correlation. So you can calculate them using FFT, and here is an example of smooth electrostatic potential and the resulting values of all electrostatic interaction energy with different shifts. And in my group, I have developed a number of methods for calculation of different types of macromolecular interactions, different flavors, electrostatics, van der Waals, hydrogen bonding, solvation, and so on. So after that, what you can do, since you can do a global sampling, unlike some other approaches, you can do global interaction sampling of the interactions. If you took the lowest energy, resulting lowest energy poses, you could actually calculate some approximation for partition function on the grid, and then get the most likely regions where the binding is happening, so which you would need to refine later. So for the refinement, we use a Monte Carlo minimization. So and most Monte Carlos are basically, the idea is the same. So our novelty for Monte Carlo is actually mostly methodological one. So we have we formulate a representation of a flexible molecule using largest, so trying to find the largest common rigid block of the small molecule, and use so-called manifold representation for the sampling of the sampling. And the advantage of this approach is actually a very low kind of parameter representation, so we use minimal amount of parameters like 3 for the rotations, but unlike Euler angle, this is a natural mapping from manifold to the Euclidean space, so we really can have like a very effective approach which has like a nice uniform sampling. So we published quite a few papers on this area, mostly again in applications to peptides and proteins, but this can be easily adapted to small molecular motion, and just kind of to show you like small movie how the minimization in the space is working. So again, more details are provided in the papers. So, and finally, the last stage, I mean, like since we were provided waters, and like as mentioned, it was mentioned before, like there was some new hydrogen bond interactions with the crystal waters. So we actually replaced all the waters and we minimized our poses. And as you can see, so in quite cases, actually, it helped to orient like the molecular groups better. So we have now, so this is the results. So we went through, so I will go through first through 35D3 C1 interaction. So our best pose was, unfortunately, I don't have RMSDs here because organizers provided us with the average RMSD. So like, so we could only tell what like how the like top pose and best poses look like. So as you see in this case, the third pose actually looks the best. It's on the right part of the picture, but top one pose, I mean, like is not bad either, just slightly tilted. So this is C225D3, the second construct. So here the top RMSD is top one, even though like in this particular case the hydrogen, I mean, like even though we did have the water, I mean, like we didn't really like, I mean, like I guess it was a limitation of sampling that it didn't flip the functional group. So in C3, 25D3 interaction, everything seems all right again. So this is like interaction with 17 OHP. So in first case, one, like again, the poles look pretty well. And in the second case, where there were several crystal structures, we were able to reproduce one of the crystal poses, even though like I think we were docking to the chain A, but actually the best agreement it seems like was with the chain B. I mean, as shown here, and but chain A and chain B were pretty close in the results, and we didn't reproduce all the other poses in our sampling. So in terms of scoring, as we discussed here, there was only 2 points. It seems like for the rescoring, again, with water, we used like energy, it's Wiener-like energy function. And so like in this case, the scoring worked. And one thing that we noticed that the discrimination between, even though the ordering was right, but like the difference between the scores were relatively small. So I guess this is more or less it. So most of the work was done by my graduate student, Dmitry Podhorny, in collaboration with David Hall and Dmitry Beglov, who helped with getting the FFT part like working, and thanks obviously for the funding from the agencies to support this type of work. So thank you very much.